Okay, everyone, welcome. Welcome to Calculus 2, right? Let me redo this, see where I'm showing up here. It's here. What I'm doing is I'm going to have to do this every single class. I have to come up here and figure out what the camera can see and make sure that I'm within frame. That way the recording will come out good. So I have this much space to work with. So the bad news is I'll be erasing more frequently. But the good news is that while I'm erasing, you can catch up. And then also everything's recorded and will be posted on YouTube later today. Okay, so I want to just give you an idea of how this is going to work. I've never used the camera before. Those of you who've had me before know how I used to do it. I'm trying this because I really want to get up in front of the board and move around. So what I'm going to do is I'm going to show you on this screen over here just what this video is going to turn out to look like. So I have a YouTube channel. How many of you already got on Canvas and watched the orientation video for this class? Okay, if you don't know what I'm talking about, you need to go into Canvas, get into the class. There's a video you need to watch. I go through the whole syllabus. I'm not going to cover the syllabus today. Then you have to do a quiz that says, I've read this syllabus, I understand the requirements of the course, and you submit that quiz. I think it's due Thursday before class. Okay, so, but this is my YouTube channel. There is a link to this in Canvas. And let me show you a video I did earlier today testing this camera out. Give it a second here. Let me just forward to this.
That's doing at the beginning, that pre-record equal to minus square root 1 plus x squared.
Okay, so it's decent quality. I mean, that's through a projector. If you're at home, I'm recording in 720p, 30 frames per second, so it's decent. If I record in 1080p, the file sizes get way too big. I think it's like over 20 gig for one class. This is going to turn out to be like almost 2 gig for one class. So I'm trying to balance how long it takes me to upload the video, how long it takes YouTube to render the video. I think if I do it this way, YouTube should render it within an hour. So, theoretically, you should be able to get to these videos, by 5 o'clock, 6 o'clock today. Okay. All right. So that's what it'll look like. The challenge is going to be that a lot of the things that I show you in this class are going to be up there. So I'm actually going to come and move the camera and put it up there. The reason why is because I also have a Cal 2 internet class, hello internet class, and they are required to watch this video. So I don't want to leave them hanging. I'm like, oh, well, let's look at this, and they're like, still looking at a blank screen over here. So I'm going to move the camera around, and I might even get to a point where I offer bonus points to people and they can rotate and be my cameraman for the day. And if I go over there, they move my camera and then they can move it back to me and move it, That sound like good? Everyone loves bonus points. We can rotate, like who's my volunteer for this class? And then they sit right there and that'll be the designated camera person. Not today though, unless you want to. No, okay. All right. So my name is Robert, sorry. Di Giovanni. And this is Calculus 2. Oh. Cal 2. So what have you all heard about Calculus 2?
Nightmare.
Compared to Cal 1, have you heard anything?
Harder.
It's harder? Y'all heard that?
160 miles per hour.
Yeah, I would agree with that. I think Cal 2 is the bigger of the hurdles. Even when you compare it to Cal 3, a lot of people say Cal 3 is easier than Cal 2. And I mean, really it's because the amount of material we have to cover. There's a lot in this class, so just be prepared. Hit the ground running, okay? That means day one, when I send you home with this homework, you do that homework, you come to class prepared the next day. You know, this is grown-up math, so I shouldn't have to lecture you about that, all right? Like I said, the syllabus is online. The video you can watch, I go through the syllabus. That's all for you to do today. I'm going right to Chapter 3, Section 5. I have lecture notes to hand to you, and we'll start, okay? Yes? Do we want to preview a glimpse into Cal 2, or just get going? What do you want to do? Do you want to see what this is about? Like, I would like to, have you respond to me this semester. That's part of the reason why I'm up here. Like my old students, I used to just be trapped behind that little podium thing. I want to be able to walk around and talk to you. So, you want a little preview? Okay. So, I forgot to do my thing. I'll do it next time. I'm going to have each of you fill out a little card and put it on the table so I can look around and see what your names are, and I'm actually going to call on you throughout the semester. So, I will never learn your names because I'm terrible with names, but at least I can say, Jennifer, what do you think? And I'm going to call people out, and you might get embarrassed, but look, we're here to learn, and if you don't know it, someone else in the class doesn't know it, and, no harm, no foul, right? That's okay. If you don't like that, you can still go to a different class, not too late. Do y'all want to move that table just a little bit? Because I'm afraid you're going to you sure? Okay. All right, so if we're going to talk about what Cal 2 is, tell me briefly what Cal 1 was about. If you could sum it up. Derivatives, right? That's why Cal 1 is called differential calculus. Differential calculus, derivatives, right? Derivatives. The main thing with derivatives, you had to learn the limit first, right? And then after the limit, you had to learn the rules, like power rule, and then the product rule, and then the quotient rule, and the chain rule, and you get all those rules out of the way. Then you start doing some applications, right? So you got all the rules that you have to be comfortable with. Geometrically, Cal 1, the idea was something like if you had a graph, you could theoretically go to this graph and pick a point, let's say A, and then you could find a tangent line right there, and that line would have a slope, and it would be equivalent to the derivative of the function evaluated at A, right? So the pitch of that line was somehow connected to the first derivative of the function. And then the second derivative told you something about concavity, which is, you're frowning or you're smiling, and things like that, right? So what that allowed us to do was take a function and find maximums and minimums, right? And then we did things like optimization problems, farmer builds a pen, things like that. We also learned implicit differentiation, which is where you have two variables in an equation. You can't solve for one of them, so you have to do this thing called implicit differentiation. And when you did that, you did those wonderful related rate problems, right? You have a cone that's being filled with a certain volume per minute or whatever, and blah, 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 right? All those problems. Okay, so that's Cal 1. Cal 2 is what we call integral calculus. Integral calculus, in Cal 1 you probably talked a little bit maybe about antiderivatives, at least in Cal 1. And so Cal 2 is going to take that idea of an antiderivative, which is the reverse process of differentiation. It's going backwards. And we call that integration. And so Cal 2 is a lot about what you can do with those antiderivatives, with those integrals. All right? Let me make sure I'm recording. I am recording. All right. So what sorts of things can we do? We take another look at a curve like this, but instead of looking at tangent lines, we cut this curve off, let's say between 2 points A and B, and we investigate if it is at all possible to find the area below that curve. And then later on, we assign some value to that area. Just like over here, this slope could represent like the instantaneous speed of something at a particular time. This area will have a certain representation, or will represent something depending on what these two axes are. You know, if this is time and this is force, like a force you're applying, then the area would somehow be connected to the total work done in moving an object from one place to another, something like that. But for us, we just want to be able to find that area. Then we'll do something like take that curve, take the same curve, and we will imagine cutting it off again, but wrapping this around the x-axis. So making it a three-dimensional object instead of two-dimensional. And so you get this like shell-looking thing, right? Maybe it might look something like, if I wrap it around the x-axis, here's the x-axis going through the middle of this. Can you kind of agree with me that that's what it would look like if I wrapped it around the x-axis? And then we can imagine, since it's three-dimensional, it has a volume, right? If we imagine that it's solid, that it would have a volume, and so we'd want to know, like, what's the volume of that object. So that's something else we do. Another application in Cal 2 is we'll take this curve and we'll imagine that it's, well, I don't have a string, but imagine it's a string and we take it off the page, we straighten it out, right? Pull it tight, lay it down, and measure the length. So that would give us an arc length. So we'll be able to take a path and we'll be able to measure how long that path is. That's actually more challenging than these other two things. And then we'll also be able to take this and rotate this around the x-axis. And instead of talking about this volume, we can imagine talking about its surface area. So like if we were to paint it, you know, how much paint would we need? Got it? You with me so far? All right. So rotate this around the x-axis. We can also rotate it around the y-axis. We can also rotate it around any line. It does not have to be the x or y-axis. I could take this curve here and rotate it around, let's say, this line right here instead. Would that change the picture? Would it be the same object? If I rotate this curve around here, would it be the same as rotating it around this? To be a little bigger, right? Which means it would have a different volume, which means it would have a different surface area. So we are not going to be restricted to just the x-axis. We'll switch our axes around. So everything I've described here is pretty much going to be the first. Let me look at the calendar here. I have the calendars for everyone. That'll take us all the way through late October. Okay, so somewhere in the neighborhood of Halloween. Okay? All of what I've said. One other thing we'll do is that we'll take a curve. This time we won't bound it. So we'll take something like this. Let me do a bell curve. You've seen these before. Right? You've heard of bell curves before? So these are asymptotes. So the graph is getting closer and closer to those dotted lines. And so the question becomes, is there an area for this? Does this have an area? Is that area underneath this curve finite or not? Or is it infinite? What do you think? It'll depend. It'll just depend on the curve. If the curve decays fast enough, then the area could be finite. If it doesn't decay fast enough, then it could be infinite or unbounded. But we'll look at these. These will be called improper integrals. Another scenario that we run into is something like this, where we have a function, let's say something like y equals 1 over 1 minus x, which looks like this is a rational function. It has a vertical asymptote at 1. So it's undefined at 1. You agree? And let's see, what's happening to the right of it? Like the right of 1. Let's plug a number in here to the right of 1. So like 2. What would we get, a positive or negative number? Negative number. And so I'm not going to go through all of it, but you get something like this on this side, and on this you get something like this. All right? That's what would happen if we graphed it. So what if I asked us to find the area, let's say from here to here? Is it possible to talk about that area? So like underneath this graph, I'm talking about this in here, and then I'm also talking about this area here. Is that infinite area or is it finite? And again, it will depend. So these are called improper integrals because you're dealing with these weird situations where your graphs go forever in each direction or have a vertical asymptote. Kind of make sense? Okay, so that'll be a lot of the, it sounds like that's like most of the class because it takes us to late October. But November is going to be where the true suffering begins because that's when we get into chapter 8. Chapter 8 is probably the hardest chapter, in my opinion. Chapter 8's, I'll just say series, sequences and series. And this is a very, very interesting chapter. The things that go on in this chapter have repercussions in other math classes, other engineering classes, things that you do here just pop their heads up all over the place. So I'll give you an example of a series. If I take something like 1 plus a half plus a fourth plus an eighth plus a 16th, and I do that forever and never stop, the question becomes, does this add up to be a number or does it become infinite? What do you think? Infinite? We'll take a vote. Let's not be afraid, right? No one's going to get so humiliated today that they're going to drop the class, right? So let's take a vote. How many of you think that this is just going to get bigger and bigger and bigger and go to infinity? Okay. How many of you think that this is going to add up to be a finite number? Okay. So it's kind of, by me asking, it's kind of giving it away a little bit because I wouldn't be asking if it didn't do something weird. This actually becomes, this is a finite number. Right? This has not become infinite. And that's counterintuitive because if you look at this, these are all positive numbers. And if you keep adding positive numbers on top of positive numbers forever, you would think that you can't have a cap to it, right? That you're eventually going to get to, if someone says, well, that never adds up past 10. You would think that eventually you would get to 10 and you just, you'd be able to get past it. Maybe, I don't know. But it turns out it doesn't. And so this is an example of what's called a geometric series, and we can actually figure out what that adds to be. We'll figure it out. Okay? And what this whole chapter really makes you start to think about some strange things. It's a lot different than the other parts of calculus where it's a lot of okay, you find the derivative, you use the rule, you get a result. This is really going to ask you to find patterns in things, and that's a lot more challenging because it's hard to teach that pattern recognition. So, okay. I'll show you another series that is very, very weird. So what do you think about this one? Does this add up to be a number? Does it become infinite? Does it do something else? 0? 1 or 0? Right? It kind of depends. Like if you just look at the first one by itself, it's 1. But if you do the first two added together, it's 0. And then you add that one, it's 1, and then 0, and then 1, and then 0, and then 1. Right? So, interesting. I wonder what it does. I'll show you something on this. Shit, see, I always do this. I start talking for 20 minutes. I don't have time for anything else later. Let's just call this S, okay? All right? Let's call that S for the sum, whatever it is. I don't know what it is. Then what's 1 minus S? Okay, it's 1 minus this, right? Which is, I'm going to put in parentheses, 1 minus 1 plus 1 minus 1 plus 1, right? Minus 1 plus dot, 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 forever, yes? All right, distribute the negative through. And what do you get? You get 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus, right? Don't you? But what is 1 minus 1 plus 1 minus 1 plus 1 minus 1? It's s, isn't it? So aren't we saying that 1 minus s is equal to s? Which means that 1 is equal to what? 1 is equal to 2s, just adding s to both sides. So what's s? A half. What? It's kind of like the average value of the two things you thought it could be, right? 0 and 1. It's like the average value. Now, I'll tell you right now that a mathematician, and in this class, we will say that this series diverges, all right? But in physics, this sum is used a lot, and they actually use 1/2 because they're experimental. When they run experiments, they get series that behave this way, and they can show experimentally that this is the result they're getting. So they use this in physics as the sum. It's kind of weird. There's another one. I'd see if I can remember. I haven't looked at it in a while. It's something like this. 1 plus 2. Oh, wait a minute. Hold on. Is it plus? Ah, shoot. I don't remember. Sorry. It's either, I think it's this. We could work it out, but I don't have time. That this is equal to negative 1/12. I want to say there are pluses between all those, but it's something that doesn't really make a lot of sense that it would be this. So, okay, so series are really interesting, and we'll get into those pretty deeply. And by the time we get to chapter 8, I said it's the hardest chapter. By the time we get to chapter 8, usually the people who are still in the class can handle it, you know, because they've proven through the other stuff that they're ready. You know what I'm saying? The first part of the class, the first, a couple of weeks, all we're going to be doing is learning how to find antiderivatives. How to do that. It's called the techniques of integration. And that's a pretty tough section also, but we'll see how you do. All right, so that's just a basic glimpse. We do some other stuff in polar coordinates and parametric curves at the very end of the term, but we only spend like maybe 2 days on that, 2 or 3 days. Please take one of these and pass these back. These are on the website in Canvas. It's the schedule. I'll let everybody get a copy. It kind of lays out the day by day, blow by blow of how things are going to go, okay? Okay. Where? Back there? Can you just hand that back, please? I'll slide those back. All right. So let's get started. Or unless there's any questions or comments. When are my office hours? Anybody know when my office hours are? I have them before this class from, I thought it was 11 to 1. 11 to 1 before this class. I'm in my office. You can walk in, you can get help. And then immediately after this class, from what, 3 to 4? Yeah. 3 to 4, I'm in my class, or in my office to help you. All right? You need more? I think I handed more that way. The notes? No? This pack of notes? Oh, man. Really? That's it? I saw notes sitting on the copier. I thought I accidentally printed them twice, but I guess someone had split my stack up. All right, well, for those of you over here, I guess y'all don't get them. Sorry. But they're going to be up here. So These are all online, by the way. These are in Canvas. I'll bring extra copies next time. These are in Canvas. You can print these out. You can bring them to class and reference them, okay? You need a seat, sir. Let's try and find you a home. Do we not have any more desks here? Well, there's a spot right here. I don't know if you want to get that close or not, but you know, can we slide this desk a little this way? Because I'm kind of pinning that camera up. There you go. Thank you. Nobody has any questions about anything? No? Anything you want to talk about before we get started? I'm wondering if this camera is going to get in the way of you guys. I don't know. You just have to let me know. Where the hell is that thing? There it is. All right, so let's begin. We're going to talk about one-to-one functions. So we're in Chapter 3, Section 5. In Cal 1, you went way past Chapter 3, so you may have seen some of this before. So one-to-one function has to pass the vertical line test, right? To be one-to-one. And if it passes the vertical line test, then that means the function has an inverse. Some examples of one-to-one functions are not illustrated here. Vertical line test, yes, it is a function. Horizontal line test, I said vertical, didn't I? Has to pass the horizontal line test to have an inverse. Okay, so the classic trig function sine of x does not pass the horizontal line test, so it does not have an inverse. Would you agree? If I look at that, it does not have an inverse. If you look at the cosine function, it does not have an inverse. The tangent function is periodic, right? Just like all the others, and it does not have an inverse because if you draw horizontal lines, you'll hit a bunch of times. And we could look at all the different trig functions. The cosecant, if you remember the cosecant was the reciprocal of sine, wasn't it? And you can actually graph sine at the same time, and remember that those little parabola-looking things were always at the peaks and valleys of the sine function. That's where they occurred. And then you had vertical asymptotes that occurred at the x-intercepts of the sine function. Remember this from pre-cal? It's been a while. Okay. Cosecant is the same as secant, except you work off of the cosine function instead. So secant, again, does not have an inverse. And then cotangent's the last one. Cotangent looks like tangent, but it goes the other way, and then the vertical asymptotes are at different places also. So I expect everyone here to be familiar with all 6 trig functions. You should know what they look like. You should know their domains, their ranges, their periods, all that good stuff. There's a set of formula sheets on the website on Canvas that you're allowed to print for this class. I think it's 6 pages. It includes pictures of all of these functions. So you just need to know how to reference it. Okay, I don't necessarily expect you to know right offhand the period of cotangent, but if you do know it, great. All right, so those are our basic trig functions. So how are we going to get around trying to come up with an inverse function for sine? Because that's what this section is about. It's the inverse trig functions. So if I know that sine doesn't pass the horizontal line test, how can I make it so that it does? I cut it off. So what we do is we restrict the sine function. In order to force it to be a one-to-one, we must restrict its domain. So here is an example of me restricting sine. So let me bring sine back in here. There's the sine curve. And what I've done is I've cut off everything left and right. I've just included the stuff between negative pi over 2 and pi over 2. Just that one little piece. If I do that, then that piece right there is a function, and it does have an inverse because it passes the horizontal line test, doesn't it? Also, what's important to keep in mind is that the entire range of the sine function is included in here. So from -1 all the way up to 1, that's all included in the picture. All right? Is that the only one I could have used, though? No. How about this? How about if I took, there's the sine function, what if I took this back piece over there? That passes vertical and horizontal line test. And again, it includes the entire range, -1 to 1. Everything's there. So why not use that piece instead? We could. There's actually infinitely many ways we could have done this. I could have taken another piece of it over there. But what we do is we have to agree as a group, as humans, as math people. We have to agree what is the piece that we're going to cut. And we all agreed that it's this one. And so with that, we can define the inverse sine function, or what's called the arcsine function. So these two notations here, right? Arcsine, or sine with a little -1, is the name of the inverse function of sine. We must restrict the domain of sine, though, between -π/2 and π/2. Everyone clear on that? The only way you can ever talk about an inverse sine function is if you're restricting the sine curve between -π/2 and π/2. If we do that, then we have the following. The inverse sine of x is equal to y. What does this mean? Arrows both ways. If and only if, that's what the double arrows mean. It means implications in both directions. So the inverse sine of x equals y if and only if the sine of y equals x. Notice how the x and y switch places there. We must make sure that the y we're talking about, which is this piece that's in sine, is between -π/2 and π/2. Now, the thing that you put inside of sine is called the argument of sine, but it's usually an angle, isn't it? Sine of an angle. So what we're saying is that angle must be restricted between -π/2 and π/2. And I think, oh, this is the other notation. This one I used the sine with the little the little -1, and here I'm using arcsine. It's just two different notations. Be comfortable with both. Here's a picture of the two together. That's just so you can see it. The red one is sine, and the blue one is its inverse. Does anyone remember the property of functions and their inverses when you graph them? Anyone?
They reflect off the they reflect off the line y equals x.
Perfect. Yes. Anytime you graph a function and its inverse on the xy plane, then they should look like reflections of each other over the identity, which is the diagonal line, which is the line y equals x. So they do look that way. Okay, so now I'm going to do some examples. Let's see how this works out here. I'm going back to my board. Let me do some of these. So find arcsine of 1. Find the arcsine of 1. So I'd like for us to be very comfortable in understanding geometrically what we're saying here, all right? Because I don't want you to just break your calculator out and do arcsine of 1. When you plug something into arcsine, right? When you plug something into arcsine, it's going to spit out what? So I'm going to write this underneath this. With arcsine, I'm going to plug in something and it's going to spit out what? So go back up to the notes and take a look. Look at this right here. We said, what do we plug into sine? We always plug what into sine? An angle, right? An angle goes into sine. So that y in the formula, right? The y in the formula is This one right here. That's an angle. So that means x is going to be a number, isn't it? So if you look on the left side of that double implication, inverse sine of x equals y, x is a number, isn't it? So anytime we're dealing with an arc trig function, this is a number, the argument is a number, and what comes out over here is always going to be an angle. So looking back up at this, if we say arc sine of 1, what we're saying is, what angle do you plug into sine, right? We're looking for the angle. That would give you the value of 1. That's what we're looking for. Now, depending on your pre-cal background, you know, that will kind of dictate how you do this. I love to utilize the unit circle because I think the unit circle is the better way to look at trig functions a lot of the time. When you're on the unit circle, all those numbers that go around at the common angles, right? Those were connected to sine and cosine, weren't they? And so what we're saying here is, where is your sine? Where is the value of sine 1? Sine is which coordinate on the unit circle?
Y.
The y coordinate. So you say, well, where's the y coordinate 1? That happens here, right? That's at 0, 1. And so we want the angle that corresponds to that point. And what is that angle? 90 degrees. So you could answer this two ways. You could say 90 degrees or pi over 2, right? Now, we don't really like degrees. We prefer to do everything in radians, so pi over 2 is better. It's not incorrect to say 90 degrees, but we kind of want to wean ourselves off of that a little bit. It's kind of like, do you still use that symbol? No? I mean, degrees, we use it. I'm not saying we don't use it. It's just not preferred as you move on. All right. What about the next one? See if you can get the next one. The next problem is, so I'm doing 3.5 example 1 right now. I know some of you don't have your notes, or don't have the notes. I apologize. How many notes do we have here at this table? Can we share one set of notes? You got, does this table have notes? Y'all don't have the notes? You have? Who doesn't? Could you hand that back? Thank you. That way y'all can at least share that. And the next one, arc sine. I use different notation though. Root 3 over 2. Okay, so next class when you have your name tags up in front of you, I'll just call on somebody and embarrass you. So today I'll let you volunteer. Anyone want to volunteer the answer? Go ahead.
Pi over 3.
Pi over 3. And that's because you're saying again, where's the y coordinate root 3 over 2? The y coordinate is root 3 over 2 here, right? Yes? What's that point? It's 1/2 root 3 over 2? Something like that. Trying to just make sure this is coming out. But wait a minute, isn't there another point over here that has the same y coordinate? Negative 1/2 root 3 over 2? That one has the same y coordinate, doesn't it? So why not use that one? I'm restricted because I'm dealing with an inverse trig function, and specifically the inverse sine. As soon as I'm dealing with inverse sine, I'm never allowed to look over here, because our angle has to be restricted between what? Negative pi over 2, where's that? Remember, negative angles go the opposite direction. Negative pi over 2 is down here, and then pi over 2 is straight up. So you're only allowed to be in the first and fourth quadrant in order to spit an answer out. So that's good because it eliminates two possible answers. Let me add a little curveball to this. How about arc sine of negative 1/2? So it's a different problem. Oh yeah, by the way, this was pi over 3, right? This angle was pi over 3, which is why that answer was pi over 3. What about this? So where is your, this is again asking, where is your y coordinate on the unit circle, negative 1/2? So where is it? Is it right here? Is that it? Yeah, that's the point, root 3 over 2, negative 1/2, yes? Okay, so what is this angle that goes from here to here? 11 pi over 6. But to get to 11 pi over 6, didn't you have to go through, isn't that bigger than pi over 2? So you can't go this way to get that answer. You have to go which way? Backwards. So negative pi over 6 instead. So even though 11 pi over 6 will still land you at the same point, that angle is outside of the domain restriction. So our answer here would be negative pi over 6. Any questions on that? That can get a little tricky sometimes. Just remember your angle has to be between here and here. Positive to 90 degrees, negative to 90 degrees, negative to negative 90 degrees. Or 0 to pi over 2 or 0 to negative pi over 2. All right, moving along. Next note, I'm now on 3.5.4. Oh, no, I'm not. Yes, I am. All right. The inverse trig function. So just like with sine, we can do the same exact thing for cosine, right? That would make sense. Except that our restriction for cosine is different. What is our restriction for cosine? The angle has to be between 0 and pi. I'll show you a picture of that in a second, why we do that. And then for tangent, we can restrict the tangent function between negative pi over 2 and pi over 2 and be able to come up with an inverse also. So sine and tangent have the same domain restriction, but cosine doesn't. All right, the remaining trig functions and their inverses can be found in the book, all right? And all their domain restrictions are in the book. So you can look through that. This is all pre-cal. There's nothing I've done so far that's calculus. Everything we've done is pre-cal. Cancellation property. Remember that, try and make this a little bigger. Remember that if you ever have sine together with arc sine, they basically cancel each other out so long as the x you're plugging in was between negative 1 and 1. And then if you do it the other way, you do inverse sine, and inside of that you put sine. It'll spit out the x as long as the x was between negative pi over 2 and pi over 2. So I think I'll give you two examples of that. I'm going to give you some examples of that, and then we'll get on to the derivatives. See, this is why I'm going to need a bonus person for the camera, because this is going to be too much of a pain in the ass to go back and forth. So I just want to show you some things that you could potentially get stumbled up on. If I say, what is, which one came first? Sine, let's do that. Sine of arc sine of 4. A lot of people will be like, well, they wipe each other out, right? Sine inverse of x should just be x, so the answer should just be 4, right? That's what people will do. That's incorrect. Why is that incorrect? It's got to be between negative 1 and 1. And that's, think about this though. Why is it messed up? What does inverse sine of 4 mean? It means what angle do you plug into sine to get 4? And that's not possible because sine's bounded between negative 1 and 1, right? You're never going to get 4. So this just doesn't make any sense, right? So this basically would have, doesn't exist, domain restriction, fail, whatever, all right? It doesn't work. The next one that you could potentially get tripped up on would be something like this. Because again, you look at the property, you're like, they wipe each other out, right? Yeah, they're gone. You just get what, 7 pi over 6? But that's not right either. Because the angle that comes out of an arc sine must always be between negative pi over 2 and pi over 2, right? Always. So I can't say 7 pi over 6 because that's outside of that bound. Agreed? So how do I do this? What is the answer? This one you can do just by taking it piece by piece. Look at the inside. 7 pi over 6 is here, isn't it? That's 7 pi over 6? What is sine of 7 pi over 6? So what is the y coordinate at this point? Negative 1/2. Yes? So what I could do is I could rewrite this problem as arc sine of negative 1/2. And now this inside piece doesn't matter anymore. And what I'm doing now is I'm just looking at this and I'm saying cut off this left side because I am now in a domain restriction because of the arc sine. And I'm saying what angle spits out, what angle do I plug into sine to spit out negative 1/2? And that was this angle, wasn't it? We just did that a little while ago. And what angle is that? Negative pi over 6, right? Negative pi over 6. So this, we're just back at the problem we did a second ago. Any questions? All right, let's look at derivatives. So I'm not going to move the camera because I think my internet students could just look on the notes. It says here that we really, since we've studied inverse trig functions in pre-cal and we're in calculus, what we really want to do here is start to talk about the derivatives of the inverse trig functions, which a lot of times in Cal 1 you don't cover, but depending on what school you are coming from, some Cal 1s would actually talk about the derivatives of the inverse trig function. So some of you may have already seen this. But in order to do derivatives of the trig functions, inverse trig functions, we're going to have to take note of two different things. You're going to need to know how to work with reference triangles. And you're going to need to know how to do implicit differentiation. So I'm putting here, these are the skills that are going to be required for us to be able to do what we need to do here. All right, here we go. 3.5, example 2. I would like us to take y equals the arc sine of x and find y prime. All I'm asking here is for you to tell me what the derivative of arc sine is, right? Arc sine of x, what's its derivative? That's all I want. Well, you could just look at your formulas in the back, in the formula sheets, and it would tell you, but I want to know where that formula came from. So I said you're going to need to be able to do these two things. Draw a reference triangle and use implicit differentiation. So let's see how this goes. First thing I'm going to do is I'm going to rewrite the equation, right, that we're looking at. And I'm going to take sine of both sides. And that's because I have an equation. I can basically compose both sides of the equation with sine. So we are taking sine of both sides, right? We are not multiplying by sin, right? Sin is not a number. That's not the operation we're doing here. We're actually taking sine on both sides of the equation. Now, what will happen on the right-hand side? What will sine of arc sine of x be? It'll be x so long as x is between negative 1 and 1, right? So we have this. So there's my domain restriction. So keep in mind that x has to be between those two numbers as we proceed. All right, now the reason I did this, sine on both sides, is because I actually do know what the derivative of sine is, don't I? From Cal 1. The derivative of sine of something is cosine of it, right? So I'm going to take the derivative on the left side and the right side implicitly with respect to x. So derivative of sine of y is cosine y, drum roll, y prime, times y prime. Now, where does the y prime come from that I'm multiplying here? That's chain rule, right? You have to then go inside and take derivative of what was inside sine. In this case, derivative of y is not 1, it's the derivative of y, which is y prime. So there's the chain rule on the left side. On the right side, what is the derivative of x with respect to x?
1.
That is 1. Now remember, what is it we were trying to solve for? Y prime. Here's y prime. Can I get rid of the cosine y on the left side? Yes, divide both sides by it. So y prime is equal to 1 over cosine y. Now, you could argue that you have an answer because you have y prime. The problem is that y prime is in terms of y. Most of the time when we took derivatives of functions like over here, we had y, our answer would be like in terms of x, right? If you had y is x squared, the derivative was 2x. We want our derivative to have x in it, not y in it. So somehow I need to recover x from this information. And this is where the reference triangle comes in. So I've already done the implicit differentiation in the problem. Now I'm going to use a reference triangle. So watch how I'm going to do my reference triangle. What I'm going to do is I'm going to go back to the point in the problem where before I took the derivative where I had some information that connected x and y together. Specifically here, I had that sine of y was x, right? Now I'm going to draw an arbitrary right triangle. And this is going to be what I call my reference triangle. Now, if you look at this equation and write it down like this, but rewrite x as being the fraction x over 1, then you could say sine of an angle is equal to, what is sine in terms of a right triangle? Opposite over hypotenuse, right? So couldn't you say that sine of the angle y is this opposite side over this hypotenuse? So if I take that equation, I could translate it into this picture. Do you agree? That equation becomes that picture. Any questions? Come on. It's your money. It's your time. Well, maybe it's taxpayers' money. I don't know, but no questions? No one's going to be brave. Okay. Sine is that. Sine of y equals x over 1 means I can draw that picture. Now, look at what we want to find. What do we want to find? Cosine of y. And you know what? Isn't 1 over cosine of y, isn't that just secant? That's just secant y, isn't it? So I would like to know what secant of y is. Secant of an angle is the reciprocal of what? Cosine, right, from that. What's cosine of this triangle? It would be adjacent over hypotenuse. I want hypotenuse over adjacent, don't I? So I need to solve for this side of this triangle. But if you have two sides of a right triangle, you can always get the third, can't you? Can I trust that you could solve for this on your own? What is it? Maybe I should solve it just because it's day one. All right, I'm going to call it a for adjacent side. A squared plus x squared is equal to 1 squared. Pythagorean identity. Can you solve for a? Square root both sides. Do I take the negative and positive case? No, just the positive because a here is a positive number, isn't it? It's the length of the side of the triangle there. So this A is this. And that's it, right? So what is secant y? We said it was cosine is adjacent over hypotenuse. Secant is hypotenuse over adjacent. So shouldn't I just take 1 and divide it by that? And that's the answer. Question? I see squinting and wrinkled brows, but I'm not getting any questions. That's a formula. It's in your book. It's also on your formula sheets. The derivative of the arc sine of x, which isn't up here anymore, the derivative of arc sine of x is 1 over the square root of 1 minus x squared. Okay? That's what it is. Now you could do the same exact process to find the derivative of arc cosine of x, arc tangent of x, all the other three, arc secant, arc cosecant, all of those, you could do the same exact process. They all require some setting up, implicit differentiation, reference triangle, and final result. Okay? Let's see what we have next. Oh, we have another example. I really hope this blue marker comes out good. Do you mind hitting that light back there? Let's turn that light on. Yep, there you go. Yeah, that's good. All right, so let's look at this. What is the derivative? Find d dx, that means the derivative with respect to x, of arc sine of the square root of x squared plus 1. So I showed you what the derivative of arc sine was, right? We just did that. And I'm telling you that the other formulas can be found on your formula sheet and in your books. So you are now allowed to use them, right? You're allowed to use the formulas. You don't have to show it like I did each time. You just needed to see where it came from. So we do have now arc sine of something, but to take the derivative of it means now we have to apply the chain rule, don't we? So we want to be able to kind of like cover up everything here and just be like, okay, what's the arc sine, what's the derivative of arc sine of this, according to the formula? 1 over the square root of 1 minus this squared, right? That's what it is. So I'm going to write that down. Using the chain rule, the derivative of this is 1 over the square root of 1 minus this whole quantity squared. And you know what, can we make this, hold on, let's make this a minus 1. Just make that a minus 1, please. Change the problem. Are we done? Is that the derivative? We're done? No, because now chain rule says you've taken care of the arc sine. You must now take the derivative of what was there and tack it on through multiplication. So what is the derivative of the square root of that stuff? I'm going to do it kind of slower. It's 1 over 2 times the square root of x squared minus 1 times the derivative of what's inside there, which is 2x. So I'm just finishing off chain rule on this. The derivative of the square root of that is this. The derivative of what's inside is this. So if you need to go back, brush up on your derivatives. The only thing that's new today is this part right here. Everything else is just chain rule you should have seen in Cal 1. This 2 and this 2 cancel. Let me see if I can do any more cleaning up here. How about we square this square root? What would happen if I square that square root? Goes away, and then the negative distributes. So you get negative x squared, and then plus 1, and then you had a 1 out here. So plus 2. Yes? And then on top, anything left on top? That x out there? So we should have the x way out here, from out here, over square root of 2 minus x squared. That's this right here. And then we still had this one right here, square root of x squared minus 1. And you could go even further and put these two together. Since they're both square roots, you could take the insides of them and multiply them together. But I'll just say that's good enough. Any questions? All right, now I just told you again that the formulas for these are in the book and on your formula sheets, but there's one in there that I'm just going to jot down on the side here, because this one's going to come up a lot for us. The derivative of arctangent of x is 1 over 1 plus x squared. The derivative of arctangent of x is 1 over 1 plus x squared. Put a big star next to that, because that will follow us for the rest of this semester. That one comes up. So I'm doing example 4 now. If y is equal to the square root of the natural log of arctan of x, I want us to find y prime. I'm going to let you try that for a few minutes. See how you do with that. See if you can find that derivative. Go ahead. Sorry, you're okay. Wow, this thing's really having trouble focusing. Y'all can talk to each other. That's okay. See if you can get it. I'll be right back. I'm going to try and grab some black markers.
So 1 over Then derivative, which is
I'm going to start writing the solution up here. All right, that's the uncleaned up version of the answer. There's not a whole lot you could do to clean this up either, because you just multiply all those together and just leave them down there. So let's talk about this. What is the derivative of the square root of something? 1 over 2 times the square root of that something. Then you're done with square root. Okay, what's the derivative of natural log of something? 1 over that something, right? Done with the natural log. What's the derivative of arctan of something? 1, or arctan of x? 1 over 1 plus x squared. And you're done. That's it. Okay, let's do the next example. Example 5. So for example 5, you'll notice that this equation cannot easily be solved for y. And we ran into this in Cal 1. We ran into equations that cannot explicitly be solved for y, and in that case we could not find the derivative explicitly, we found it implicitly. So we just want to do implicit differentiation on this. So the derivative of the left side, what is the derivative of arc sine of something? 1 over the root of 1 minus the something that we have, which in this case is xy squared, but then squared. So that's the derivative of arc sine of this junk right here, right there. But then chain rule says we now need to take the derivative of what's in here. And that's going to require we do a product rule, isn't it? So I have times, here comes my product rule. And my product I'm talking about is the product that occurs between the x and the y. So what's the derivative of x? 1 times y squared plus, product rule, derivative of y squared. 2y, I heard it, y prime, then times x. So applying the product rule to this expression results in 1y squared plus 2y y prime times x. Hopefully that rings a bell again from Cal 1, the implicit differentiation on that. You have to be very careful with that y prime, right? If that doesn't pop out, you're doing something wrong, and you never have y prime in here, and then you can't ever solve for it. Does that take care of the left side? Yes. So equals on the right side, what do we do? Term by term, right? Derivative of 1, 0. Here, another product rule. So what is the derivative of x? So it's the same thing as the left side, except instead of y squared, I've got y. So it'll be y plus y prime x. Now what we would need to do, what that I'm not going to do, is we'd actually need to free y prime. We would need to free it from the parentheses, which means we'd have to distribute this ugly thing through to the two terms here, which would just be, what, the first term? I'll just write the first one down. It'd be y squared on top of that. Right? And then the next one would be all of this junk on top of that. And then equals the other side. And then what you do is you get all your y primes to one side, everything that doesn't have y prime to the other, and factor y prime out, and divide through. So if you need to go back and review implicit differentiation from Cal 1, go ahead and do that. Because if you go back and review, you'll realize that solving for y prime was always kind of not the harder part of the problem, but the more tedious part of the problem was getting the y prime alone. Any questions? What are we doing on time? Got about 30 minutes? Okay. I need to be quick here. We're going to example 6. Example 6, 3.5. A rocket is fired straight up with a speed of 1,000 miles per hour. An observer who is a mile away from the launch point is tracking the rocket with binoculars. At the moment the rocket is 3 miles high, how fast is the observer's angle of inclination changing? What is that in degrees per second? Okay. So I'm going to draw a picture, because that's the way we do related rate problems. That's what this is. So I'm going to draw a picture. I'll put my rocket right here. So here's the launch pad. My rocket is going to be fired straight up like this along that line. My observer is on the ground, I'm assuming, perpendicular to that launch point. And the rocket is moving along that vertical line. Yes? So my rocket is at some point like this, moving this direction at 1,000 miles per hour. Agreed? That red point's moving. My observer is how far away from the launch pad? What is it? An observer who is a mile away, so 1 mile, is watching this thing go up, right? So depending on how you were taught related rates, what I say may kind of sound like new to you. I always told my students with related rates to do what? 2 different pictures, right? One picture of what's happening in general, and another picture of what's happening exactly at the moment we're talking about. So I'm going to let this one over here be my general picture. And then another picture over here is going to be the exact moment in time. With my moment in time picture, what changes is that I can fix the rocket, can't I? I can fix the rocket to be how high? 3 miles. Which creates a right triangle. So now what? I guess I'll draw a line connecting. I'll make it dotted, connecting my observer. We want to know how fast is the observer's angle of inclination changing. That's this angle right here. We want to know how fast that's changing. Agreed? Let's call it theta. So we actually want, what is it that we want to find? How fast is the observer's angle of inclination changing? So we don't want theta, we want d theta dt. We want to know how quickly the angle is changing with respect to time. Right? It's one thing to figure out what theta is, right? If I give you a triangle that's fixed, right, like this, can you tell me what theta is? Could you actually find that angle? Yes, because it's fixed. But we know that the rocket has never stopped. We're trying to find at an instant how fast that's changing. So we don't want to know a static moment in time. We want to know how things are related to each other as they change. So we want this. When do we want this? When the rocket's 3 miles high, right? So what we need to do is come over here to this picture, and we need to label the distance between the rocket and the ground as a variable, because it's changing throughout the problem, isn't it? So why don't we call it h for height? The height of the rocket? Over here, at the moment in time, h is 3, isn't it? So what I could say is that I would like to know how fast the angle's changing when exactly at the moment that h is 3. Does that make sense? Now, it's also wise to write down the information that you're given. What is it that you're given in terms of a rate? Are you given a rate here, a derivative? Anyone? The speed of the rocket. The speed of the rocket. The speed of the rocket is telling you how fast h is changing with respect to time. So it's dh dt, isn't it? So we're given that the change in h with respect to time is 1,000. And I believe that's all of the information that I really need to actually do the problem. So does anyone remember what the next step is once you've kind of written down, drawn your pictures, written down the things that you want to find, the things that you're given? Find an equation, connecting. I like to always say, try and connect that variable and that variable together. Connect theta to h. If you can connect theta to h, you're done. You have an equation. So you can't look at that picture, you have to look at this one. What equation relates theta and h together? Tangent. Tangent. Because now you could say sine, couldn't you, or cosine? Well, sine, not cosine. Cosine has this and this, and that doesn't have h. But sine you could say, right? But you don't know what the hypotenuse is. You know this side. It never changes. So using tangent, we'll make sure that that doesn't ever change. So the equation that I'm going to use, I'm out of room. The equation that I'm going to use for this problem is that tangent of theta is equal to what? H over 1? H over 1? Okay. H over 1. Now, how would you do this in Cal 1? At this point, once you have this, what would you do? Derivative on both sides with respect to time, right? That's the way you do it. So up to this point, like, what's new? I haven't shown you anything new, have I? There's nothing new. But this section is about what? Inverse trig functions, right? So check this out. What is it that we want to know? D theta dt. Wouldn't it be nice if we had theta by itself? Yes? So before I take a derivative here, let me just get theta by itself by doing what on both sides? Arctangent on both sides. So if I take the arctangent of the left side and I take the arctangent of the right side, what comes out of the left side? Theta within the domain restrictions that you can read about in the book. I'm not going to stress that too much. Theta would be this. And the right-hand side is arctangent of h. So there's good news and bad news here. The good news is that if I take the derivative on both sides with respect to time, what's the derivative of theta with respect to time? D theta dt, and that's exactly what I want, and I'll have it solved for already, won't I? The bad news is that I need to be able to find the derivative of an arctangent. But that's what we did today, right? We know the derivative of arctangent is right here. Yes? So the point is that if you didn't look at this stuff in Cal 1, you would have taken your derivative here. And it would have taken you some time to get d theta dt by itself, and you'd have to work out a lot of stuff. Let me finish and I'll show you. But with today, we take the derivative. I always use a squiggly line to let people know I'm taking the derivative with respect to time. D theta dt Anybody from another class ever like have a way of representing the fact that they're taking the derivative? Like any notation? No? Just a d on the outside? Yeah. I just want everyone to know that I went from here to here, I took the derivative implicitly. So I use a squiggly line to let everyone know I did that. All right, so the derivative of the left side is that. What's the derivative of the right side? And be a little careful with this. 1 over 1 plus h squared. Good. Times? Times dh dt. Times dh dt. Chain rule, right? The derivative of arctangent of something is 1 over 1 plus the h squared, but then you always have to take derivative of what's inside, and because it's with respect to time, the derivative of h with respect to time is dh dt, so it pops out. Got it? Now, can we solve this right now, straight away? Do you know what h is? Yes. 3. Do you know what dh dt is? Yeah. We're done, right? I mean, that would be pretty easy to plug in. Now, let me contrast that with, well, let's actually get the answer and then I'll come back. 1 over, what's this going to be? 10 times 1,000. Why did I put plus? No idea. 1,000. Which is 100 d theta dt is 100 what, though? Radians per second, degrees per second. So let's see if anyone can remember this. What is time measured in this problem? This 1,000 was 1,000 miles per hour, right? Miles per hour. So our time increment is hours. What is our theta increment? What is our theta measurement? It's an angle, right? Radians always. You convert to degrees later if you want, but your answer is going to be in radians. So this is 100 rads per hour. 100 radians per hour. If you say 100 degrees per hour, it's incorrect. Now, what was the second part of the problem that I told you I wanted to know? What is that in degrees per second? Because I wanted to make sure you knew how to convert that to degrees per second. Because if I tell you, look, there's an angle, it's changing 90 degrees per second, then I think everyone understands like 90 degrees is this, 1 second is about that. So you kind of have an idea of what 90 degrees per second is, right? But 100 radians an hour, do you have any idea how fast that is? Not really. So let's convert it to degrees per second. So how do we convert this? 100 rads over 1 hour. So this is, we call this dimensional analysis. All you're doing is changing units. So let's go for the hours first. How can we get hours to seconds? 3,600. 3,600 seconds in 1 hour. So we put 1 hour up here. We put 3,600 seconds down here. Good. And then how do we get to, right, our hours will cancel, and so we'll have seconds on the bottom. How do we get to from radians to degrees? 180 degrees is pi over 2, or sorry, pi radians. Pi rads, isn't it? A pi is 180 degrees. So anytime we want to go from radians to degrees, we multiply by. So I'm going to put rads here, and I'll put degrees up here. So that way the rads will cancel. And then I use that conversion. Pi down here, 180 up here. Do you agree? Pi radians is 180 degrees. The rads cancel. And so let's multiply that. Someone on their calculator, take 100 times 180 divide by 3600, and then divide again by pi. Let's see what someone gets. Anyone?
1.59.
Approximately 1.59 degrees per second. Anyone else get 1.59? Yes? Okay. 2 people got it. We'll say that's good. 1.59 degrees per second. You kind of have an idea of what that is, you know, like 1 degree a second. It's not too fast, is it? All right, whatever. That was only the speed at that instant. An instant later, it's a different speed, a different rate that it's rotating. All right, there's a homework assignment at the back of this on the bottom, homework, all right, which I do want you to do, but there's some other stuff I want to do. I still have you for 14 minutes. This is, was that it? Yeah, that was where I said we hadn't done anything new, right? And then what I did was I took arctan on both sides, and then it came out super clean, didn't it? But in Cal 1, what we would have had to have done is we would have taken the derivative here. We would have had derivative of tangent theta, which is derivative secant squared theta, then chain rule d theta dt, so there's our d theta dt, and then the right side would have been dh dt. And see, the challenge here is that, yes, you can get d theta dt. Yes, you know dh dt, but what are you going to need in order to figure this out? You're going to need to know what theta is. So then you have to go back to that general picture, or not the moment in time, and you have to actually figure out what theta is. And then figure out what secant of that is, and then to square it. And it's just a little more work, where doing the arctan on both sides right away, we didn't need any information about theta itself. All we needed was h and the speed. We were done. What's that saying? There's more than one way to skin a cat, I guess. I've never understood that, but you know the saying? That's kind of the same thing. And there's a more efficient way to do that problem, and it's the way we did it. So what I'm going to do now is, like I said, I'm doing this as an internet class also, and they have homework that's based on the book. And so for the next 15 minutes, 12 minutes, whatever it is, I'm going to do some problems that I think are good, that are related to the homework. You'll see problems like this too. It's not your homework problem exactly, problem for problem, but it'll give you some idea of what to expect. And hopefully what you'll see with this is that it can get a little more complicated than what I showed you in class. Here's one. I'm going to put number 2 only because, again, my internet students, when they do their homework, that's going to be number 2 for them, but that doesn't relate to you. All right, so they're given this arctan square root 1 minus x over 1 plus x. And they're asked to find y prime. So this is just chain rule. That's all this is. So let's see how this works out. What is the derivative of arctangent of something? Uh-oh. One over 1 plus whatever was in it squared. Well, that's nice, isn't it? Because it's going to square that square root. Times now chain rule. We have to take derivative of what was inside the arctangent, which is a square root, right? And the derivative of the square root of something is 1 over 2 times the square root of that something, which in this case is 1 minus x over 1 plus x. So So that's the derivative of the square root of this junk right here. And then continuing chain rule, I have times the derivative of what's inside of the square root. And what am I going to need in order to do that? Quotient rule. And I'm not going to work through it. You can do quotient rule on the side, do your f prime g minus g prime f all over g squared, figure all that out, and clean it up. You should get negative 2 over 1 plus x quantity squared. So lots of good things happen. Things cancel with the quotient rule. You just get a negative 2 up there. So the reason I'm showing this to you is because this cleans up quite a bit. And I want to make sure everyone's comfortable on the cleanup for this. So I'm going to first start by putting these two together. So how do I put those two together? Turn that 1 into 1 plus x over 1 plus x. Get a common denominator and smash these together. I'm going to do that without showing the work. Again, I just want you to know what I'm doing. Putting these two terms together. That'll leave me with a 1 over, and when you do that, you get, it really cleans up nice, 2 over 1 plus x. On this next term over here, or these next two factors, I should say, do you agree that that 2 and that 2 would cancel, but you still have a negative 1 up there? Okay. On this one, do you agree that the square root of a fraction is the same as a square? You could do the square root on top and bottom separately, right? I could break this into 2 square roots, like square root up here, square root down here. And then you have 1 over a fraction, which is the same as the reciprocal. So this whole thing's just going to flip, and it's going to turn into this. Square root 1 plus x over square root 1 minus x. And then this one out here times, there was a negative 1 up top still, 1 plus x quantity squared. Anybody see anything?
The reciprocal of the leftmost.
Wait, hold on a second. Hold on a second. Yeah, no. Yes, you can, but look at this right here. You were talking about this one? Yeah, just flip this one up. I thought I did that already. Okay, these two come together, I have this, right? On my next step, I can just flip this up. So instead of writing it all out, because I only have about 8 more minutes, I'm just going to do the 1 plus x up here over the 2, like that. And then notice that one factor here cancels with one of the factors here. So we get, okay, what's still on top? Negative square root of 1 plus x over, on the bottom, I still had a 2 down here. I had square root of 1 minus x, and then what's still down there next to that? 1 plus x, right? Is there anything else I can do? It'll go a little bit further. Yeah, this right here and this right here, if you look at this square root as really being raised to what power? 1/2. Then this is like x to the 1/2 over x to the first power, and you could subtract, 1/2 minus 1, and right, and you could simplify that. So when I simplify that, I get a negative 1 on top. The 2's still out there. 1 minus x is there. When I do these two together, 1/2 minus 1 is what? Negative 1/2. And so it should be 1 plus x to the negative 1/2, but then we drop it back down. And so it'll be 1 plus x to the 1/2 on the bottom instead. This is just algebra. I understand I still do see some looks of concern on your faces, but it is algebra, and I just want you to make sure you go and try and make sure you can do this, okay? And one last step. These two roots can come together because they're both square roots and it's multiplication. And that means I just multiply these two inner pieces together, don't I? And what happens when you take 1 minus x and multiply it times 1 plus x? You get 1 minus x squared. You get the difference of squares. So your final cleaned up answer would be this. Right there. So the purpose of that problem was just to show you you got to be able to do the algebra in here. So there can be quite a bit sometimes. Okay, something else. How am I doing? Still got 4 minutes. How about this one? May I erase? Still getting this? Everyone done? Okay, next one. This is going to be it's going to seem completely unconnected to this. This is their problem number 6. Something like this. What is tangent of secant inverse of 5? So what I'll do is I'm going to call this piece right here U. This has to do with reference triangles, all right? That's the way you can attack something like this. I'm going to call that piece U. Is everyone okay with that if I call that U? All right, so I'm going to write that down. U is equal to secant inverse of 5. Now what I'll do is I'll take secant on both sides. Secant U is 5. Can somebody help me draw a triangle that represents that equation? A right triangle. What's my angle? What do I call the angle? Theta, x, y, z, what? U. Because U is this, right? Secant of an angle is 5. And 5 has to be the what side over what side? Secant is, this is hypotenuse over adjacent. Secant's the reciprocal of cosine. Cosine is adjacent over hypotenuse, so secant is hypotenuse over adjacent. So this is 5, and this is 1 right there. Now, the reason why I want that is because what is this question really asking me? What is tangent of U? Here's your picture. Tangent is this, right? So you just need to find that side, which again, you could do Pythagorean. If you do Pythagorean, it's actually this, square root of 24. So what's the answer to this? What is tangent of secant inverse 5? Well, that's the same as saying what's the tangent of U. And according to my picture, tangent of U is this side over this side. So root 24, and then you could simplify that, but I'm just going to put, what would it be, 2 root 6? 2 root 6. Root 24 is 2 root 6. God, I'm out of time. I tell you what, you're free to go. I'm going to do a couple more problems. You're not going to hurt my feelings. You go. But I wanted to do a couple more problems more for my internet students. So I will see you all next time if you want to go. I'm only going to probably go for like 10 minutes. Do the homework that was on the end of those notes. Do those problems. Make sure you do the online quiz where you say you've watched the orientation, you know what's going on in the class. Print out the notes for next section, because the next time we're covering what? 3.6, hyperbolic functions. Okay, so print out those notes. What else? I think that's it. Yeah, that's it. Really, don't feel committed to stay. I mean, I don't want you to feel like I'm going to call you out or anything. I will normally take attendance. I didn't today. But I'll normally pass this around, and it'll have a place where you initial. Start doing that next class. All right? This problem is tricky because you have a 2 in here. So the key to this problem is to recognize a formula from pre-cal, which was something like sine of 2x equals 2 sine, well, usually they use theta. Is 2 sine theta cosine theta. It's a double angle formula from pre-cal. And so if I look at it that way, this piece is like the theta. And so I will call it u again, so that this thing really looks like sine of 2u. And according to that formula, this is 2 sine u cosine u. So I just need to figure out what sine of u is and what cosine of u is. And then I'd be done. So over here on the side, I'm going to create my reference triangle. What was u? I'm not asking y'all questions because I'm assuming y'all aren't here anymore. Okay. What is u? U is cosine inverse of 3/5. Take cosine on both sides. Cosine u is, everything goes away here, 3/5. Triangle. U, cosine is adjacent over hypotenuse. So adjacent over hypotenuse. And we should be able to get everything else from that. This will be a 4. If you solve for it, this will be 4. And so when I come back over here and I say I needed to know what sine of u was, sine of u is 4/5, right? Opposite over hypotenuse. Cosine of u is adjacent over hypotenuse. I actually knew that already, but it's there in the triangle also. So this is 2 times 4/5 times 3/5. Multiply across, you're done. So what, 8, 20, what is that, 24 25ths. So sine of 2 cosine inverse of 3/5 is 24/5. Okay, I have time for one more, and it's pretty ugly. It's pretty ugly. Let me see. Hey, where are you going? I'm just kidding. All right, y is equal to, the algebra of this problem is pretty nasty. All right, so find y prime. So we have an arctangent, and inside of that we've got some stuff going on. And we have a 7 in front of everything. So the 7's just going to follow along for the ride. 7 times the derivative of arctangent of something is 1 over 1 plus that something, which is x minus root 1 plus x squared, but that whole thing squared. That's the derivative of the arctangent part. Now you have to multiply times the derivative of what's inside. And since there are 2 terms, I'll do them one by one. So derivative of x is 1 minus, now I take derivative of the square root of something, which is 1 over 2 roots of that something. But then it's the derivative of what's inside of it, which is 2x, which I think, yeah, I'll just throw it over here, like that. Whew, okay. These 2's cancel. That would be correct as an answer. I mean, as far as the derivative, that is correct. But the answer, if I'm not mistaken, that the computer wants you to put in, shoot, I didn't finish doing it because I saw how it was going to work out and I just stopped. So, but the answer that the computer wants is really, really clean. So let's check this out. What we're going to do first is take this right here, and I'll rewrite it x over square root of 1 plus x squared, like that. Over here, 1 over 1 plus, I'm going to square this, which means it's two terms, which means I have to FOIL this out. And that's going to be this term squared. Since there's a negative, it'll be this times this, and there will be two of them. So minus 2x root 1 plus x squared. Hope you understand I'm taking this times itself next to each other, and then I'm FOILing. Then the last term, which is negative root times negative root again, which is plus, the roots will square and go away and become 1 plus x squared. That makes sense? I'll ask you since y'all are here. Did that make sense, what I did? Okay. It's right there. I don't know what you're talking about. I must have been blocking it when I was standing there. You couldn't see it. Okay, so 7's there. So now I'll write down, let's see, does any of that clean up in here? The x squared and x squared is 2x squared. 1 and 1 is 2. And I have a 7 on top. So this is equal to a 7 on top. I have 2 plus 2x squared minus 2x root 1 plus x squared. That's just this part right here. It doesn't look like it's getting any cleaner. These two I'm going to put together with a common denominator. Okay? It's not ringing a bell. Yeah. These two I'm going to put together with a common denominator. So that means I have to turn this 1 into a root 1 plus x squared over another root 1 plus x squared. And then I can put them together. And so what I get out here is times square root of 1 plus x squared minus x, that's the numerator, this minus this, over the common denominator, which is square root of 1 plus x squared. We're getting close, but we're not there. The next thing I'm going to do is, since there's one term here and 1, 2, 3 terms here, I'm going to multiply this term through to each of these. And then on top, the 7 is just going to go up here. I'm just going to put a 7 and then that in parentheses. So here's where I am. On the top, 7 parentheses square root 1 plus x squared minus x. On the bottom, distributing this to the 2 gives me 2 of those roots. Distributing this to the 2x squared gives me 2x squared times the root. And then distributing this to this is where good things happen. You get the root and the root are exactly the same, so it goes away, and I'm left with, in parentheses, 1 plus x squared. I know this still looks bad, but it's actually about to get real nice. So all I did on this step was distribute a negative 2x through right there, like that. All right. Now something you can do here, it's not super obvious though. That's why I'm showing this problem, because it wasn't obvious. Is I'm going to take this term and this term, and I'm going to factor a 2 out of both. If I factor a 2 out of both of those, remember what we have on top. Don't forget about this. But if I factor a 2 out of both of those, what's left? Just the blue ones. 2, and then what's left there? The root, 1 plus x squared, and then what's left here? Minus x, parentheses. Do you see that that's the same as what we have up there? But we still have these two to work with, so we have to look at this one. Oh, wait, this whole thing and this whole thing. And what can I factor out of both of those? A 2x squared. So I pull a 2x squared out of those, and you're left with the root again, and then over here minus x. And since they all contain the same thing in parentheses, I can cancel it. Here, here, and here. They all had to contain it though. That's why I had to wait that long to cancel. And so the final result is a 7 over 2 plus 2x squared. Or if you'd like, 7 over 2 times 1 plus x squared. I believe that's the way the computer looked at it. I think the computer will take more simplified versions, but that's the one that's in my answer key on the computer. So a pretty cleaned up version. There's a lot of algebra going on in that problem, which is why I wanted to show it. All right. I'm going to kill this video.